Okay, today, as we said in the previews of coming attractions last time, we are going to prove a very important result in algorithm theory. This is a comparison sort bound. And like I said before, this proof is going to be one of the questions on the next test. I will ask you to prove this bound. Okay, so everything, so just learn how to do this. It is an important enough proof to be able to, we have to know it and we should know how to prove it. It's a very interesting proof. So the bound is any sort of n elements that is based on element comparison and exchange is big omega of n log n. Now, big omega means what? Upper bound or lower bound? Lower bound. That means that no sort algorithm can be better because it's lower. Lower is better. Lower means shorter execution time, right? There are, okay, that's a good question. The question is, are there other ways to sort that don't use pairwise comparison? The answer is yes. They're very specialized. They only work under certain very special circumstances. But there are ways to do it without comparing. Okay, so now the first part of this proof is a lemma, and the proof of the lemma is part of the proof. Okay? So the proof uses the following lemma. N factorial is greater than or equal to n over 2 raised to the n over 2 power. All right? So let's first prove this lemma. We'll start with the left-hand side. N factorial. Okay? And the first thing that we want to do is, what's the definition of n factorial? So tell me, what is n factorial? N 1 times n minus 2 times dot 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 times all the way down to what? 1. Obviously not down to 0 because if you multiply. Okay, so all the way down to 1. Now furthermore, we're also going to assume that n is even. Now if n is even, that means that n divided by 2 is an integer. Are you with me? So the proof when n is odd, you have to modify the proof a little bit if n is odd. We're not going to, we get the same result. Are you with me? But let's just assume for the sake of argument that n is even. That means n divided by 2 doesn't have any remainder. Now do you see what we've written here is not just n times n minus 1 times n minus 2. We got all the way down to the middle. You see? So n over 2 plus 1, and then n over 2, and then the next one would be n over 2 minus 1, and then some more dot dot dots, and then 3 times 2 times 1. Does everybody understand? Is everybody with me on this? So we're just writing out the multiplication that n factorial is. But now what we can do is, we know that multiplication is symmetric, right? So we know a times b is b times a. So what we're going to do is we're going to take the last term and we're going to move it over to the first one, and the penultimate term, do you know what penultimate means? Second to last. And we'll put it to the second term, and then the third from the last. And so we're going to rearrange the numbers like this. So what we have then is 1 times n plus 2 times n minus 1 plus 3 times n minus 2 times dot 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 times what? Do you see? N over 2 times n over 2 plus 1. Are you with me? Just rearranging.
So, the second half all got moved.
Yeah, did. Yeah? Is everybody clear? Now what do you know about 1 times n? Is that bigger than n over 2?
Yes.
I think so. 1 times n is bigger than. What about 2 times n minus 1? Is that bigger than n over 2?
It's not true for n.
Well,
1, but
yeah. I mean, yeah. It's hard to say, but you agree that it's bigger than n over 2, right? We can agree that. And 3. What about 3 times n over 2? Is that bigger than? Sorry. Yeah. What about 3 times n minus 2? Is that bigger than n over 2? Yeah. What about n over 2 times n over 2 plus 1?
yeah.
That's bigger than n over 2, right? Because n over 2 plus 1 is bigger than 1. And so that's, are you with me? So look, what do we have here? We have a product of n over 2 terms, each of which is greater than what? N over 2. So what is that? So this is greater than or equal to what? To the n over 2, n over 2 to the n over 2. Now, do you agree? This shows how really big factorial is. Factorial is really big because it's big. It's bigger than n squared. It's bigger than n to the n. It's bigger than n over 2 to the n over 2. It's really big. Is everybody? Okay, so that's a lemma. So we're going to use this lemma. Now comes the key idea of the proof. If we're going to compare, if we're going to sort a list of n elements by doing comparisons, basically all sort algorithms are finding the permutation of the elements in such a way that they are in order. Are you with me? By comparing, by doing pairwise comparison. So you can always represent the algorithm, you can always represent the comparisons in what is called a decision tree. Now this decision tree is for a little short list of 3 elements, A, B, and C. And that on the root, that A colon B, that means we're going to compare A with B. And so if we compare A with B, that's either what? It's either A is either less than or equal to B, or it's what? Greater than B. Let's suppose that it's less than or equal to B. If A is less than or equal to B, then the left child of the root has B colon C. That means let's compare B with C. Now, if B is less than or equal to C, what have we discovered? We've discovered that A is less than or equal to B, and B is less than or equal to C. Therefore, what? Therefore, A is less than B is less than C, and ABC is sorted. Are you with me? On the other hand, if we compare A with B, and we know A is less than or equal to B, and we compare B with C, but now suppose we compare B with C, that means what? B is greater than C. Suppose B is greater than C. Now, do we know what order? No, we have to compare what? A and C. Now, if on the other hand, A is less than or equal to C, then we know it's ACB, but if A is greater than C, then we know it's CAB. Is everybody clear on this? Because in both of these cases, A is less than or equal to B. The question is where to put the C. Does everybody see how that worked? And similarly for the right, if A is greater than C, so it might take just 2 decisions to sort this list, but it could take as many as what? 3. Are you with me? It might take 2, it could take as many as 3. Yeah? So because it could take as many as 3, that's the maximum number of decisions is 3. So do you see that 3 is the height of that tree? The maximum number of decisions is the height of the tree. And that's how many statements have to execute in order to sort it. Are you with me? That would be how many? Regardless of whatever the algorithm is, you got to make these decisions, right? And how many leaves do we have of this tree? We have 6. And why are there 6 leaves?
So it's 6 possible ways that they can be
There's 6 possible ways to order A, B, and C. In general, how many possible ways are there to order a list of n elements? No. If you have n elements, how many possible permutations? How many possible ways are there to order them? Only one of which makes them sorted. How many possible ways? N factorial. Are you with me? This is just the case for n equals 3. Is everybody clear? So if you had a whole bunch, you could imagine a big decision tree, binary decision tree, with all these things. And the thing of it is that the number of leaves is going to be n factorial, and the maximum number of decisions is going to be the height of the decision tree. So look, so what we note here is that 2 to the 3 is greater than or equal to 6. Because 8 is greater than or equal to 6. And why do we say 2 to the 3? Because if we have a decision tree of height 3, what's the maximum possible number of children? 8. Do you see? So here in figure B, the maximum number of decisions is 3. The number of leaves is 8. So in this particular case, it's 2 to the 3 is greater than 8, which is 8 is greater than or equal to 8. But now we know Is everybody clear on this? So the relationship between the number of leaves and the maximum number of decisions. So what do we know in general? In general, there are n factorial leaves in the decision tree to sort n elements. Are you with me? And furthermore, we know a decision tree of height h has at most 2 to the h leaves. See here in part B, the number of leaves is 8. Here in part A, the number of leaves is 6. Are you with me? So what happens, so we know a decision tree of height h has at most 2 to the h leaves. Can't have more. All right? So basically, what do we have to have then? Here's the key idea. What do we know then about the decision tree to sort n elements? We know that 2 to the h has to be greater than or equal to what? N factorial. Now, is everybody clear on this? 2 to the h, the height of the decision tree, has to be greater than or equal to n factorial, because n factorial is how many leaves, and 2 to the h has to be greater than or equal to n factorial. That's going to be where we start our proof. So here's our proof. Now watch this. This is so clever. We're going to start with 2 to the h is greater than or equal to n factorial. Well, you've got some math majors here. What happens if you take the log base 2 of both sides?
You just get h on one side and g of n.
Log of n factorial. So h, so we know that h is greater than or equal to log n factorial. Right? Are we good? Okay. And now we use our lemma. What was our lemma? N factorial is greater than or equal to what? 2 factorial to the n over 2. Yeah? By the way, we're also using the monotonicity of log. Do you know what the monotonicity of log is? If A is greater than B, then what? Log A is greater than log B. So that's monotonicity. This is similar to the monotonicity that we did in formal methods, actually. If P implies Q, then P and R implies Q and R. So, but only instead of and R, it's log. You see the concept of monotonicity? Okay. So that implies what? To the n over 2, exactly. But now, obviously, what are we going to do? We know what the log, now a little more math. What is the log of something raised to a power? What's the log of A to the B?
Just n over 2 times.
B times the log of A, so it's what? So h is greater than or equal to n over 2 log n over 2. Are we good? Okay. But now look, you guys, what did we say h is? H is it's the number of comparisons that you make. So any algorithm that you do is going to have to make comparisons. The question is, how many comparisons does it have to make to sort it? Now, it could be less, but it is at most, so h, the height of the tree, is the number of decisions it takes to permute them to get them in the right order, to sort them. All right? So, well, if h is if h equals the number of decisions, then what are we saying? The number of decisions is what? Is greater than, the number of decisions is greater than or equal to n over 2 log n over 2. See, it's greater than. There's this lower bound. It's got to be greater than that. See? Okay? But now that we have this greater than, what's the definition of big omega? It's that what we're saying is that the number of decisions equals what? Big omega of yeah, this is
n log.
yeah, right, well, another step. So the number of decisions is big omega of n over 2 log n over 2, but we know that big omega of n over 2 is just a constant, and log of n over 2 is 1/2, it's a log, you can, does everybody agree that you can get rid of the constants here? Okay, so property of omega, dropping the constants. The number of decisions is big omega of n log n. So I don't care how clever you are with your algorithm, you can't do better than this. And so we have found some of the ones that we have investigated are at that lower r n log n. So you'll never find a way to sort of order n. Can't, mathematically impossible. We just proved it. So it's amazing. It's a proof that you can't do something, which is kind of amazing because, you know, how do you know you can't do that? Maybe you just didn't try hard enough, you know. How do you know you can't make a compiler that will actually automatically detect whether the program will halt without actually executing the program? Mathematically impossible. Okay? Does everybody see? So this you need to be able to just reproduce. This is such an important result that you just need to be able to reproduce it, and I'll ask you to do that as one of the questions on the next test. Yeah.
What about the lemma?
The lemma is part of the proof. And you need at least one drawing of the decision tree. just one drawing to explain height, you know.
So lemma and the decision.
Yes, the lemma, you need to include the lemma. You need to include one little decision tree thing to make your point, you know, and then just reproduce this. So this is all just, now that you know that you have to do it, everyone always gets this one. Let me say now that we have now sort of like gotten through the beginning of the object-oriented design patterns and the C++ stuff, how all that stuff works. Now we're finally going to get the rest of the course. We're going to do a lot of programming. I don't think there's going to be any more written work. So this is all going to be programming. Well, there is another paper, but you're right. Okay, but we're going to start. This is the start now of really doing a lot of data structures. Now, you guys have done linked lists, I think, a little bit. Now we're going to do them a lot. Okay, so the first data structure that we're going to look at now in this next season of data structures is going to be mutable lists. All right, so what does the word mutable mean? You can change it. Yeah, it means that you can change it. Some of you guys are in some other courses where we... What about in scheme? Are those lists mutable or immutable? In scheme, whenever we built them, whenever we returned a new... Not all of you guys have had programming paradigms, but do you remember? Anyone who did?
If they're...
I mean, how did we return a list? We had to build it. So they are immutable. They are inherently immutable. So these are kind of a little bit different. These are mutable. That means we can change them. Okay. In other words, to reverse a list in scheme, you actually have to build a new. You don't change the list. You build a new one. You cons the whatever, and then you build a new one. You return a newly created list. But because in scheme all parameters are called by what? They're called by value. Yeah, in functional programming. Anyway, so but these lists are mutable. And now here's another thing. Oh, what are the 3 goals of this course? Data structures, object-oriented programming, and C++ programming. Okay, now the data structures part of this, we're going to do 3 different versions of linked lists. The first version that we're going to call classic. The reason it's called classic is because this is the way it's almost always done. Okay. Now the other 2 ways are a little bit unique to the way we do things because we have some separate goals in this course other than data structures. But when we say classic, we mean this is the way it's usually done. So for example, if you have, if you're ever going to have like an interview for a coding job, questions about linked lists are very common for you. They'll say, well, how would you do this to a linked list? And they'll ask you to, do something. Do some allowed. This is the way. This is what they will expect. These are the kinds of things that they would expect you to know. All right. Now, so here, let's start off in Figure 6.1. Here we have a picture of a linked list, and the list has elements 9, 2, 4, and 7. And basically, here's the code for it. So you see the little rectangle on the left, the little one with it's just the one little pointer. Okay, that is called underscore head. And underscore head is a pointer to the node that has the 9 and then the pointer to the 2. So we see here in this figure that a node, okay, and we're going to call this L node for a linked list node. L node has two parts. What are the two parts? The first one is called what? Underscore data, and it has type what? Type T. So this could be, in this particular example, it looks like T is a what? Int, but it could be a link to doubles or objects or CA metrics or okay. So and then underscore next. Now what is this L node star? That means underscore next is a what? Pointer to a node. Does everybody see that? So that's a pointer to a node. And then underscore head for the whole list, that's the one on the left, that is also a what? Pointer to a node. So does everybody see how this C++ code matches that picture? Are we good? Yeah.
Is that the first one?
Yeah, underscore head is the first one, yeah. All right, is everybody good? Now, I hasten to add, oh here, actually let's think about this. Suppose you wanted to write an algorithm that would append a value to the end of the node. How would you do that with a linked list set up like this? What would you have to do?
You have to find the one that's pointing to a null pointer and then switch the...
Yeah, and how would you get to that one that was pointing to the null pointer? How would you get to it?
Go through the list.
You'd have to start at the, you only have head, underscore head, so you'd have to start at this, and you'd have to, in a loop, go down to the end, and then once you got to the end, boom, okay, so can you think of a way to, that would be big theta, oh, by the way, that would be big theta of what? Of n, where n is the number of elements in the list. Can you think of a way to do that, big theta of 1?
You have
the tail.
tail.
Yeah, you could have, instead of having just a head, you could have an underscore head and an underscore tail. Are you with me? Then, and this, I've seen this before. I've seen people do this. And the advantage is, now to do append, it's big theta of just 1. Is everybody clear on that? Okay? But it would require an underscore head and an underscore tail. So that would be the advantage. But now here's another very clever way to do it. There's a clever way to do this without having a head and a tail. You can do this with just one tail. Do you see? So you don't even have underscore head, you have underscore tail. But underscore tail points to this. But the thing of it is that instead of the last one being nil, or being nil, the last one does what?
Points back.
Points to the first one. Now underscore tail gets you to the tail with just one reference, and it's only big theta of 1 to also get to the head, because that's just underscore tail dot or arrow next. Do you see how that works? So this is also very common. This is called a circular linked list. Is everybody clear? That's a circular linked list. Okay, and the advantage is you have access to both the head and the tail, big theta of 1, and you only need one pointer to define the whole list. Now, here's another thing. Sometimes you want to be able to move, if the operation that you're doing, you want to be able to move backward as well as forward, then it's also possible to have what's called a doubly linked list. Are you with me? So a doubly linked list, not only do you have an underscore data and an underscore next, here in the C++ code, what else do you have? An underscore previous. So now there's 2 pointers per node, and this allows you to go backward. See, so if you have an algorithm that you think that would be advantageous, you could set up your linked list like this. So this is a doubly linked list. Now, does everybody see? So the node 4 underscore next points to the node 7, and underscore previous points to node 2. But of course, when you do operations on your list, you've got to take care of all these. It's a little more complicated, but you can go back. That lets you go backward. And obviously, if you can have a circular list and a doubly linked list, what do you suppose you can have? A circular, yeah. You can have a doubly linked circular list. And this is quite common, actually. I've seen, all of these are, the reason I'm showing these to you is that these are all common. Yeah.
So, are these just like better for certain circumstances?
They are. The question is, are they just better for certain circumstances? And the answer is yes. I mean, it just depends on what you think you're going to need to do a lot. If you're going to need to like go in reverse order a lot, that's your application, then maybe doubly is the way to go. Yeah.
Okay.
Doesn't the fact that there's like tons of pointers pointing in every which direction means it costs more energy, memory? Sorry.
It does. Yeah. The question is, does that take up more memory? The answer is yes. But you know, pointers. But typically pointers, these numbers, they could be like, the data part of the node could be really, really big, in which case the pointers could be a small fraction. But here again, it depends on your application. But the answer is yes, it does take more memory. And also, oh, and here, there's one more little thing that's common that you should at least see. And that is, sometimes you set up a doubly linked circular list with a head node. Now, the reason you would have a head node is because it can simplify the code. You see, it can simplify the code. So what you have is the list is a pointer to the head node, and then the head node points to the first element of the list, 9, 2, 4, 7, and then the 7 points back to the head node. And the reason it can simplify the code is because you know, even if the list is empty, there will always be at least one node, and you don't have to check to whether or not underscore head is nil, ever. Do you see? So so you don't have all these extra tests, you know. So this is also common, yeah.
With the data just being null.
The data would be empty. I mean, there would be nothing in there. Yeah. You would never set it to anything. Yeah, in the head node. But you would know, so in your code you would not have, you will see that here's the one we're going to use. We're going to use A. Okay, just because it's the simplest one to set up. But now we're going to have to have some big theta of n operations because we're not doing any of these other ways of setting up the list. So this is our C++ code. So underscore head is a pointer to a node, and that's in the class for a linked list. And then underscore data, a node has two parts: an underscore data and an underscore next. So that's what we're going to do, and the project is list L. Now, so here in figure 6.2 shows the advantage of having a head node. You see the empty list for a list without a head node, the pointer is nil. Actually, in C++ it's null pointer, N-U-L-L-P-T-R. Okay, we'll sometimes just call it nil. But then, on the other hand, even if the list is empty, there is at least one head node. So this is what an empty list looks like in a system where you implement a linked list with a head node. Does everybody see what we're saying, how that works? Okay, so now in figure 6.3 is our UML diagram of our list L project. So list L is the next one you need to set up. All right? And there's two classes. There's the class for a list and a class for a what? And a node. Are you with me? So the class for the list is list L. The class for a node is L node. And they're templatized, C++ template type. And you see the underscore head, that's a private member of list L. And you see the L node, there is a underscore data, which is type T, and underscore next, which is a pointer to an L node. Is everybody clear? And do you know, here's this symbol. What's this? What was the triangle? What was the triangle symbol? The open triangle symbol in UML. What did that, you know, with? Inheritance. That's inheritance. But now what, do we have a new symbol here? You see this one? Here it's this solid black diamond. This is, does anyone know what this is called?
Like has
The black solid diamond. It's called, it's not inheritance.
like contains.
Yeah. It's called class composition. Okay, it's class composition. So this red, the red box is saying that, is noting the fact that a list has a pointer to a node, and then the blue box is saying that even a node has a pointer to a node. Do you see how that, does everybody see how that matches? So this is has a as opposed to inheritance, which is what? Is a. So here it is. Look. So that inheritance has that open triangle symbol. The relationship is a. And you know, in our shapes one, our rectangle is a shape, is a abstract shape. But here what we're doing is class composition, and the symbol is the solid diamond, and that relationship is has a. So these are the two main primary, most important features of object-oriented design: inheritance and class composition. All right? So this is object-oriented design. That's the second goal. Okay? Now what let's do is, before we actually take a look at some code for list L, let's do a demo. Okay, so here's our demo, and our project now is list L. So we'll run this, do a little demo. So here it says there are 0.4 mutable lists. Oh man, look at this menu of options. First, set first, prepend, remove first, clone, clear, concatenate, append, remove last, remove value, zip, unzip, reverse, length, length 2, max, max 3, contains, equal, right, right 4, quit. Maybe we should just quit right now. Okay. So let's start by how do we get something set up in the first place? Let's prepend. How about? Let's do P for prepend. Prepend. Oh, now this is lists of integers. So let's prepend, I don't know, say 30. And now which list do we want to prepend it to? Let's just say list 0. So now if we do W for write, and we write list 0, watch what happens. See, it gets printed out as a 30. And by the way, what do you suppose happens if we do write and we write list 1, which we haven't? What do you suppose will come out? It'll be the empty list. Okay, so they're initialized to the empty list. Does everybody see how we did that? And now let's do some more prepending. So let's prepend, let's say 20 to list 0. And now let's write list 0. You see how that's 20, 30? Okay. And now what else can we do? We can let's do F for first. List 1. Oh, list 1. I didn't mean list 1. Just kidding. List 0. So the first element is 20. Does everybody see how that worked? And so if we look at list 0, it's still 20, 30. Now, and what do you suppose set first does? Set first of what integer value? Let's make it 50. Set first of which list? List 0. Now if we write list 0, what do you suppose is going to happen? No, it just set it. It didn't prepend it. Is everybody clear on that? It sets it. It doesn't. Is everybody? Okay, so that's so that we have set first, prepend. And how about if we clone? So let's do O. And let's clone which list? Let's clone list 0. And we'll clone it to list 2. And so now if we write list 0, that's 50, 30. If we write, did we put something in list 1? I guess we didn't. And if we write list 2, that's 53. So it's cloned. Does everybody see what clone does? And now what about removing first? Let's do I. Remove a first from which list? Let's remove it from list 2. And it says 50 was removed. And now if we write list 2, what happens? It just has 30. Is everybody clear?
And when you cloned it, it's not pointing to the original list anymore.
That's a good point. To verify whether to verify that it made a complete copy, that's called, by the way, that's called a deep copy. If we write list 0, we see that it still has 50, 30, so that didn't change. So that was a good question. You see, it wasn't just the same list. It made what we call a deep copy. All right. Now how about concatenating? Actually, let's change, let's set the first, let's make this 40 and set that to the first of list 0. Now let's write list 0 and let's write list 2, I guess. Wait, and now let's concatenate these. So T, concatenate which list? Let's concatenate list 0. No, let's concatenate list 2, the suffix list. So this is the list that's going to be in the back, with list 0. And oh, what do you think happened?
2 as
Does 2 have the 30, 40, 30? Do you see what we're saying?
yeah.
Let's write list 2, 30, 40, 30. And now what do you suppose happened with list 0?
Bigger.
It did. Watch. So this is called a cut concatenate. It actually cuts it and puts it. It doesn't copy it over. Does everybody see how that, did everybody see this demo on concatenate? This is a cut concatenate. Okay? And now, so list 2 has these elements on it. Oh, 22, which list? 2. Has 30, 40, 30. Now, we also have a remove last, okay? So if we do S for remove last, and remove last from which list? List 2. Now if we, does it tell us which one was removed? Oh, it did. Yeah, 30 was removed. So now if we write list 2, then there's 30, 40. Is everybody clear? Now let's take a look. Let's add one more. 30, 40. Let's do an append to list 2. Oh, append integer value 2 to list 2. Okay, so now if we write list 2, there's 30, 42. Now let's do the, how about if we do reverse? R, reverse, list 2. And now if we write list 2, what should it be? Obviously, 2, 40, 30, so we can reverse. If we want to know what the length is, G for length, length list 2. The length of the list is 3. Does everybody see? Max, what about M, max? Maximum of which list? List 2. What's the max?
40.
40. Oh, how about N, contains? Search for what integer value?
30.
Okay, 30. List 2. The list does contain 30. Let's do another contains. Let's search for 99 in list 2. The list does not contain 99. Is everybody good? And see if two lists are equal. L, the first list, 0. Second list, 2. The lists are not equal. Obviously, if we compare 2 with itself, list 2 with list 2, the lists are equal.
What does length 2 do?
That's a different version of length. Well, yeah, I have 2 different versions. And there's also 2 different versions of right. And 2 different versions of max. We'll get to that. Okay, does everybody see, here's an important one, remove value. Let's write list 2. Now, check this out. V, remove what integer value? First of all, let's remove something that's not there. 99. Remove from what list? List 2. Now you see, if we write list 2 again, nothing got removed because 99 wasn't there. On the other hand, if we want to remove the value like 40 from list 2, and now if we write list 2, the 40 was removed. Is everybody clear? Does everybody see? So that has to go down and search for a value and remove it. Okay, now we quit. End of demo. Okay, so that's the demo. Now, this demo, is probably going to suffice for the other lists, I mean, as well. All right. So now let's start taking a look at let's do some code walkthroughs. And of course, a lot of those functions that I demoed in the DP4DS distribution are exercises for the student. And now this next assignment is really long. There's a lot of those methods that we demoed are exercises for the student. So let's take a look now. First of all, let's take a look at the structure of a node, of a list and a node. Now here in figure 6.4a, we have a detailed rendering of a list and a node. So you see the outer box on the left, it says my list. So if you have a variable of type L node and my list is of type L node, that box represents my list. And then a list has a what?
Data.
No, it doesn't have a data. A list has a what? It has an underscore what? Underscore head. And underscore head is a what? Pointer to node. So you see the inner box is my list dot underscore head. Does everybody see that? Are you with me on this? Dot underscore, because you know it's a class, the way you get to an element of a class is dot. Are you with me? So that's dot. And then my list dot head is a pointer, so star my list dot head is what? What it points to. Are you with me? So the big outer box on the right is star my list dot underscore head. Is everybody clear? Because that's what my list dot head points to. All right, and then, but now here's the thing. The data part of that is my list dot underscore head arrow underscore data. And the next part of it is my list dot underscore head arrow underscore next. All right, because what is the definition of this?
Same thing as the my list dot head
It's
parentheses dot.
Yeah, it's the star, right?
Yeah.
It's the star and the dot together. That's what it is. So if you work that out, that's what that is. Now, what we're going to do is, it's important to see, I think it's important to set things up like this so that you can see how to access each particular element of a class. But it's really awkward to draw that all in that level of detail. So frequently, in what comes up next, we will abbreviate the rendering without that additional detail of those different parts that are actually inside the class. Does everybody see what we're saying here? So in fact, those pictures that we looked at before, you know, they were actually abbreviated. You know, there was this abbreviated rendering, okay? But this is really what's going on in the code, is in part A. So let's take a look. Oh, I didn't, was there a prompt that said empty? I don't remember. Maybe not. When I did that demo,
It was a clear.
there was a clear, but was there is empty?
No.
I don't think this one got exercised at the top. At that, I don't think is empty got exercised in the main program. But there's one that's used internally. Is empty. True is returned if this list is empty. Otherwise, false is returned. And then remember how we wanted to know what first was? Remember we queried first. Precondition, this list is not empty. Postcondition, the first element of this list is returned. Remember, it echoed it out. Okay. And length, we did length. Postcondition, the length of the list is returned. Okay. And then remember we did max. What does max return? Type what? No. T. It did in our demo, but T in general. All right, is everybody clear on that? So returns type T. Contains, remember we did contains, and it said what? Yeah, it's contained, or no, it's not. So what does contains return? Boolean. Equals. True is returned if this list equals list RHS, the right-hand side. Otherwise, false is returned. And what does it mean for two lists to be equal? They have to have the same number of equal elements in the same order. Remember we compared a an empty list with a non-empty list, and the program didn't crash. They were not of equal length, but it just returned false. So they have to be equal length with equal number, equal elements. That's going to be one. That'll be tricky for you guys to do.
Is empty?
No. Equal. Equals is tricky because you got to take into account the lengths. Okay, and you want to do it efficiently. Okay.
The elements within them have to be in the same order?
Yes. They do have to, the elements, to be equal, the elements have to be in the same order. Right. Okay. So we're overloading the operator, the streaming operator, and then toStream. Do you remember how let's just take a look at this toStream, and remember how the list got printed out? It was a parentheses. The empty list was just a parentheses. The list with one element had a parentheses with no comma, with an element with no comma. And then if it had more than one, then it had a comma where it needed it in between them, but not a comma after the last one. Remember all that, how that worked? Well, here's the code to do all that. So what's the first thing that comes out? First we stream out the left paren, and now check out this for loop. For node star p. So what does that mean? P is a pointer to a node. Are you with me? Gets what? What's it initialized to? Underscore head. And now what are we checking? P is not equal to the null pointer, so that's, are you with me? So while it's not, and then what happens each time we go through the loop? P gets what?
Next.
P arrow next. So it'll keep getting next until it's what?
No point.
Until it's a null pointer. So we know that inside the loop, P is pointing to a node. So we know that there is a P arrow what?
Data.
There is a P arrow data, and there's also a P arrow what? Next. So if P arrow next is not equal to the null pointer, that means we're not at the last one. And we have to print out the what? The P arrow data and the what? Comma. Otherwise, we just do what? Print out the P arrow data. And then at the end, we print out this closing. Yeah? So does everybody see how that works? So these are the kind of manipulations when you do your loops with the linked lists and stuff. This is how to set up a for loop. This is a typical way to set up a for loop to go through, work your way down the list. Instead of I++, it's P arrow next. Are we good? All right. See you all next time.
Great.